It is, and the recording is on, and those are my first words, that the recording is on. All right, so last time we went through light, the uses of light, the instruments we use to look at light, so now we're going to look at light. Any questions from previous sessions, or things that came up from last night after you had fitful dreams of not being real? No, nothing? All right. You won't know it, right? Yeah, you wouldn't know it. All right, so into atoms and what makes light. This is the light, electromagnetism, is the force particle associated, or force associated with the particle photon, and it is one of the four forces. Sometime I'm going to give a talk, I think will be what's so heavy about gravity or something like that, and talk about the weirdness of gravity. There are some who can make an argument that gravity is a different kind of force from the strong, weak, and electromagnetic ones, but we're not going to go there now. We're just going to stick with light. So Joseph von Fraunhofer, early 1900s, took the solar spectrum, and people knew that they could make rainbows out of light, but he really expanded it out and detected these dark lines, different patterns of lines for different elements. And the elements each have multiple lines that they interject into the spectrum, and we'll talk about the difference between absorption and emission lines shortly here. But this really says it all. This opened up our study of the universe in a way that basically allows us to see the chemistry of the universe in places we'll never get to. So it's absolutely an amazing gift. So here's solar spectrum greatly magnified. We get broad and narrow and bands of different intensity. These are all absorption bands. So you have this background continuous spectrum that comes from a gas under pressure that's just heated, and then something is taking away some light, absorbing it before it gets to you. So you're not seeing information necessarily about the underlying illuminating sun. You're seeing something about the envelope of stuff right above the big bright part. That's the technical term, big bright part. So the atom is a positively charged nucleus. You have protons, which are heavy, and neutrons, which are heavy. They only differ by the charge and mass of an electron, and another little particle. Won't go into that. And this is where most of your mass is. Your electrons really don't contribute much to your mass, but you have a cloud of this negative charged electron around it. So if you take a little dot on a page, you have 10 million atoms that could fit and end across a dot on a piece of paper, much more so on a screen like this because it's blown up. You go super magnification, you've got a cloud of electrons and a little teeny nucleus inside. You got a huge volume of nothingness until you get down to the nucleus itself. And if you recall, we started the course a year plus ago with Powers of 10 video, and the narrator called that a vast inner space, and pointed out that regions of high activity and low activity alternate as you go from the very tiniest all the way up to the very largest in the universe. And so we are now working with the electron cloud surrounding the nucleus in our atoms. If you took out all the electrons, you would compress down tremendously. So we'll get to what neutron stars are, but a neutron star is a large object that basically is that. It is all the atomic material left over crammed down to the point where the electrons are jammed back into the protons for the most part, and you don't have any space in between things. So the mass of a star is crushed down to a few miles in diameter. That's a lot of compressibility. So usually we have the same number of neutrons and protons and electrons as a happy electrically neutral, stable in most cases, atom. If you are missing neutrons and you have an isotope, or if you have additional neutrons, you have an isotope. If you are missing electrons or have extra, you have an ion. It's very hard to make isotopes change because it's very hard to get into affect the nucleus. Natural radioactivity does that, but you have to wait for it to decide to pop a particle out and change the configuration inside the nucleus. The number of protons is what gives you the element that you have. Everything else can come and go. The number of protons give you the element. So here's our electron cloud to scale. Way down here is a little football field, and a grape seed on the 50-yard line is a way to visualize how truly tiny this nucleus is compared to the sphere of electrons around it. So here's our hydrogen has 1, helium has 2, carbon has 6 protons, and you have just hydrogen for a proton. If you have a proton and a neutron, you have deuterium. If you have a proton and 2 neutrons, you have tritium. And deuterium and tritium are radioactive. The neutron wants to leave. But when you get helium, then it becomes stable to have 2 neutrons in there. C12 is normal carbon, but if you have C14, over time, the extra neutrons will pop out, and from that we can get the carbon dating of organic materials as C12, C13, C14 along the bottom there, isotopes of carbon. Phases of matter is just based on temperature, going from a solid to a liquid to a gas as you heat it up to, we start to ionize atoms all the way up to fully ionized plasma with all the electrons pulled away at some pretty high temperatures at millions of degrees. So colliding atoms can stick together. There are stable configurations of electrons. Even though the atom is electrically neutral, something deeper is going on into the orbitals around the nucleus, and if you have full versus empty or partially full orbitals, the orbitals want to be complete. So there are some elements like oxygen that do want quite violently sometimes to share electrons with other elements, so you have combustion occur easily with oxygen. With atoms or elements that are content with the number of electrons that they have in their orbitals, you don't get chemical reactions very easily, like helium and neon and xenon, the noble gases over there. So we do make a little picture in our brain that looks like little solar systems. That really isn't it, but I don't want to get too deep into quantum mechanics here. We're just worried about light and where light comes from. So the electrons jump between the orbitals. These are different energy levels for electrons. When they jump up, they need energy to do that. That energy has to come from someplace outside. When they fall back down to a lower orbital, getting closer in our little cartoon picture to the nucleus, they give up that very same amount of energy, but only that energy. And the electron, when it leaps, doesn't go from the one orbital up or down by traveling through the intervening space. It vanishes from the one and reappears in the other instantly. So that is the quantum leap, from which we get a television show with Scott Bakula from way back. But this quantization, this discrete levels that electrons will inhabit inside the atom was the big breakthrough that solved all sorts of problems. One of which is the what's called the ultraviolet catastrophe, that as you increase frequency, you should just get a lot more energy, up to infinite amount of energy into or out of atoms, and that just wasn't seen. And it was Einstein who helped solve that problem, saying, well, it's quantized discrete amounts of energy that are accepted, nothing else. That solved that problem and launched quantum mechanics as a science, even though he had issues with that for the rest of his life. So the very simple version, summing that all up. So if there's an atom sitting there and light comes through of maybe a nice continuous range of frequencies from some hot, dense ball of gas like the sun, then the electrons will get excited, they will absorb just the energy that helps them hop up to the next level up, or the next levels up, and they will take that energy out. So they remove that from the light coming through. Because that light is missing, when we're beyond that absorbing gas and look at the original light source, we don't see those bands. That dark line left is the absorption line that we saw earlier in the spectrum.
What happens to that photon when it gets absorbed?
It stays, the energy remains in the atom. The atom acts like a little battery.
The particle itself.
Hmm?
The particle itself, does it go out as a much lower energy, basically, redshift, almost infinitely redshifted, or what goes on to,
We'll talk about that in emission, but it comes out exactly the same way it came in. Yep. Unless there's a way for, if it's 2 hops up and it can hop all the way down, then you get the combine of 2 original photons in. The 2 hops up will come out as 1 hop down. Yep.
Okay, so the photon stays there until it...
Yep. So the absorption line and the following emission line are exactly the same. So you can do the chemistry of an atom either way. But we're just about to get to that. Yep. So that removed energy is these dark lines. They are specific to that exact frequency, that quantized amount of energy that's taken out. And because every element has its own configuration of orbitals around it based on the proton count, then you have exact fingerprint for each element and molecule. Molecules do it too. That's out there. So now going to your emission lines, the energy is stored inside the atom with the electrons in an excited state. They're hopped up to a higher orbital, and spontaneously at some point they're going to release that, cool, and you get emission lines. So when they hop back out, you get bands. See, I got that exactly where the original absorption lines were. Now it can be 1-to-1, or like I said, you could have this one and this one, this one and this one combined to pop out to give you that one, or something like that. It can be a double jump or a triple jump all the way down and release a higher energy, because purple is higher energy, so there's more energy here, photon, but that's the math of it.
If the released photon has the same energy, why do you get an absorption line? It seems like in a steady state, some would be absorbed, but others would be emitted at that same frequency, and therefore they sort of cancel each other out and wouldn't have an absorption.
Right, but you're talking the direction of the light. So if I'm looking at the sun right now, there's a cloud of gas in the way, then I'm looking at one tiny little direction. When the photon comes out, it comes out in any possible direction. So if someone off to the side in any other direction will see an emission. But yep, good point. So directionality matters there.
So it redistributes all that energy sort of equally over a sphere.
Yep. And going to last night's talk, that is an increase in entropy. So you have lost information from that one direction, you've now turned into a unidirectional emission of energy. So you've done what thermodynamics also dictates, because you've had a transfer of heat. Yeah. And time ticks forward. All right. So here's a light bulb shining, and if you're over here with your telescope looking at the light bulb, you see a nice continuous spectrum. But if we got this cloud of gas around, and the telescope's looking at that light, you'll see the missing lines. If you're off someplace inside looking at any of these particles and ignoring the light source itself, you'll see the emission spectrum. And so that's what we get from the sun. The sun itself is this continuous light source, but the gases right above the surface and outward all contribute to what's removed. That's why, looking at Tabby star from last night's astronomy update, if we're looking at the gas clouds in between our solar system and the Tabby star system, you can get all sorts of information from that. We just need more data and more precision to be able to measure what's going on there and separate that from what's happening right around Tabby star itself. So that's why it'd be nice to find some nearby stars that are also passing through whatever gas cloud is there. So here's some example fingerprints. Helium's pretty simple here. We got red, yellow, some greens and blues. Sodium's just got a couple yellows here. Neon has got a ton of lines way down here in the red. And so, except in the cases where we have an excited gas inside emitting ultraviolet light that then makes a phosphorus glow in a certain color in sort of cheaper neon tubes. When you have pure gas tubes, you can get different colors from the gases inside. So in many cases, the multicolored advertisement tubing or decorative gas tubes that we have out there, kind of ubiquitously called neon tubes, are actually other gases to get the other colors. So helium definitely would have a bluish, greenish cast to it. We already know sodium vapor streetlights are those salmon-colored, yellowy pink ones that we have out there. Which, in the days that that dominated, that put that light up in the sky, and if you wanted to filter that out of your observatory, you could stick a sodium or mercury vapor, because those are the white bluish ones, which had distinct emission lines, and you can filter that out and see the sky from your backyard telescope. With LEDs act much more like that, putting out a broader continuum of light. They have their certain region that they're heavy on, so you get the color, but they're much harder to filter. So as an astronomical community, we're not happy with the LED switch, even though that's saving a lot of energy, and those bulbs last much longer like that. So here is an example of Orion Nebula. So we have a big bunch of gas and some dust in interstellar space. We've got a whole bunch of young stars pumping out lots of energy, especially up in the ultraviolet, and that excites, there's energy there to excite atoms all over the place. And you have, here's some neon, ionized neon, helium, ionized oxygen, helium. There are astronomers whose lives are reading this pattern, and they can glance up and just know it. They can see instantly all the chemical elements present in a spectrum. I do not have that skill. Nowadays there's software for that, because you can take a spectrum, put it onto a CCD chip, and then send that over to software that just maps it all out and does it for you, because these are all so absolutely predictable in their separation. And if you happen to find somehow lines that no one ever discovered before, then you could go to the lab and start exciting gases at different temperatures and eventually find it. The physics here in the lab will be the same as the physics across the universe. It's one of the great assumptions in astronomy that we make, and so far has been held true.
Does the strength of the emission line correspond to the amount of the material there? So you can say this has twice as much hydrogen as oxygen or something because that line is much wider?
There is some, you would have to know what because the broadness of the band can be related to the element, it can also be related to the strength of the magnetic field, it can be related to the pressure that the gas is at, it can also be spread by the rotation of the star, it can give you a spreading of the two things because you'll get a redshift one way, a redshift the other way, so the two combine to make it look broader. So if you had like gases near the surface are rotating quickly, the gases further out are just drifting through the solar system, you would have a broadening for that. So that would all confuse the picture. But if you knew some of those elements and then you knew what equal amount all look like in thickness, you probably could. Yeah, you'd have to separate all those other contributing factors out, but yep.
This assumes you're in the same reference frame as the...
Yeah, we'll get to Doppler shifting too, yep. Because even with Doppler shifting, if you're in a different reference frame, you'll see a velocity shifting of everything relative to each other. They're all the same.
What about thermal velocities? Is the temperature of the emitter?
No, well, the temperature of the emitter gives you an overall amount, and we'll talk about Wien's law shortly. So you'll get more illumination in certain parts of the spectrum based on the temperature.
The width of that line?
But the width of the line wouldn't change here. No. Yep. So radiation temperatures. We heat an object, atoms begin to move around faster and faster and collide. Electrons get knocked to higher and higher levels. The more heat we add, eventually that begins to glow and emit radiation. So there we go. We're already there. Thank you. So blackbody radiation is the amount of radiation emitted with a peak wavelength, which is temperature dependent. So here's the whole spectrum. But something that's really cool, like 5,000 degrees is not really cool, unless you're in Phoenix in August. You get a peak that's down here in the reddish part of the visible spectrum. Object 6,000 would be more in the yellow-green. Object at 7 or 10,000 degrees would be up in the blue ultraviolet area. Maximum wavelength, this peak, is 3 million divided by the temperature in Kelvin. Gives you the frequency of the peak wavelength. Kind of very simple relationship there. So that's when we look in the sky at night and see stars that are reddish, like Betelgeuse or Antares. Look reddish to our eye. They are red giants. They're cooler. Their peak spectrum is down here, and our eyes predominantly pick that reddish color. If you look at Sirius or Rigel and Orion, then you would have blue or white stars that are hotter, and their peak energy is tilted towards the blue end there. So it's kind of like a cooler poker here. Further from the fire is glowing mainly in the infrared. As you heat it up, it begins to glow red, then orange, then a kind of a white orange as it gets really, really hot and is about to melt. So we kind of cartoon-wise in society think of red as hot, as a hottish color, but it really isn't. In the red to blue spectrum, red is the cool end of things. So even you have a peak frequency. Everything that has a temperature does. And so humans are peaked way down here, where 15,000 degree Kelvin star be way up here in the ultraviolet. So if you look at the peak, you can get the temperature. You don't even have to use the spectrum. But then if you look at the spectrum, different classifications of stars have different temperatures And so you can compare the two. You can see whether the peak matches the spectrum based on the fingerprint. Now you have two ways to determine the temperature. And that's one of the things, again, going back to last night's Tabby star, that if it has swallowed a planet and is artificially bright, artificially hot, but its chemical fingerprint is that of a cooler star, we'll know that when we get more data. And then we'll be able to also figure out its distance more accurately, or go backwards. Once we get the distance, we can figure out the temperature that it should be and separate out the in-between gas and dust and tighten in on what may be happening at that star. So again, if you get multiple avenues of figuring out the same thing about an object, then you have more confidence that each technique is working properly. The microwave background radiation temperature of the universe is even shifted further down here. So we're in the infrared. That's why night vision goggles work to find bad guys out in the field when the military is looking for it. All right, so Wien's law gives you this peak radiation. That's the 3 million divided by the temperature in Kelvin. The total amount of energy that you get from an object at a certain temperature is called the StefanBoltzmann Law. And so it's the area under the curve. So this is calculus coming in here. Looking at how much area under here tells you how much total energy is coming out. So our sun is kind of average. A cool red dwarf star is putting out less overall energy. You're putting out a lot less energy than the sun. And a big hot O-type star will be pumping out a tremendous amount of energy, not only in higher frequency, but overall a lot of energy. So yeah, that's enough. So this leads to, kind of hinted at O-type stars and G-type stars, and let's see, K for Tabby star last night. But spectral classification is a nice binning way to see what we see in the universe and put them into quick categories that communicate to other astronomers what a whole bunch of things about a certain star. K-type or G-type star is going to have a whole bunch of attributes that are very similar from star to star because it's based on the mass of the star and the age. We'll get to that. So how do stars have a higher peak emission, more overall energy? And that's what we're interested in. Stars typically range from about 2,000 Kelvin surface temperature up to 40,000 Kelvin temperature. The 2,000 Kelvin are very red. The 40,000 are blue-white with a lot of their energy high up in the ultraviolet beyond what we see with our eyes. The Balmer series is another group of standard lines that we see from the hydrogen, helium, and a little bit of other metals that are found in stars. And when you look at these lines as a set, you can figure out the temperature and figure out the stellar classification pretty well. So cool stars have weak Balmer series lines. There's less ionization going on because the amount of ionization gives you a different fingerprint versus neutral stars. Hot stars have weak lines overall. Everything is ionized. Medium stars have strong lines. Sort of the correct amount of energy for these lines to be caused for emission, absorption right over the star. So during the late 1800s, astronomers trying to get a hold of what's going on didn't really understand what was going on with the temperature and the size of stars. And they created an A through Q classification system, just straight on through. They were wrong as what's going on, but kind of like hoarders, we never throw anything away in astronomy. So we kept as many of the letters as we could and just reorganized them to match a correct hot to cold spectrum. So OBAFGKM goes from the hottest to the coolest of main sequence stars, O being very hot and being the very coolest. And a way to remember that in the olden days was, oh, be a fine girl, or oh, be a fine guy, kiss me. Of course, you could get in trouble with the current political world. So we did enter cooler classifications, R and S, were favored down in the cool end of the spectrum for some very unique metal lines that came along. So it became, oh, be a fine girl, kiss me right now, sweetheart, which again, it's got issues. So, oh, brutal and ferocious gorilla, kill my roommate next Saturday became the more neutral way to, more politically correct, to kill roommates, yes. So, oh, be a fine girl, kiss me right now, sweetheart, whatever, looks like this. The O's through the M's and down. And we've subdivided the classes, 0 being the hottest end of each letter to the coolest being a 10. So an A3 is a little hotter than an A7. And we can get a nice little picture of the classifications like that. Our sun then is a G2 star with a temperature of 5,800 Kelvin on average. More recently, R&S has been studied more and further corrected. We've brought in carbon stars in 2018 that take up much of the R and the N. So we now have C-R and C-N for carbon stars. These are really, really blood red stars when you look inside. We've also added LT and Y, red and brown dwarf stars. And the S's kind of fall between the M and the C-type stars. And I don't have any mnemonic that would help you figure all that out. You'll just have to put it in your smartphone in a note and look it up. So all that kind of is historical now. We can get more information from the spectra by looking at, like I said earlier, how these lines shift in mass. Up or down. So just like you hear sirens of a fire truck coming by, or just every car that passes you on the road is you've got higher frequency followed by lower frequency sounds, because the lines, the wave fronts get compressed in the direction that the object is moving and stretched out in the direction behind. The speed of sound doesn't change, and the speed of light doesn't change when a car is driving along or a star is moving through the universe relative to you, but the wave fronts compress and pull apart. And so we hear that as a higher frequency sound as it's compressing, and a lower frequency sound as it's stretching out. Or in light, that's a bluer frequency when it's compressing and a redder frequency when it's stretching out. So if you didn't take this into account, a star that's pulling away from you very rapidly gets stretched out a lot, would look a lot redder. You would think it's a cooler star, erroneously, but it's all caused by velocity. So we can get the velocity of stars, gas clouds, even galaxies, and the rotation of individual stars by the spreading out of their emission lines, and the rotation of galaxies as well. We can look on the right and the left side of a galaxy out there and see the en masse average hydrogen and helium emission lines shifted one direction, and on the other side shifted the other direction, and figure out how whole galaxies are rotating. And from that we can get rotations of galaxies and figure out that things are going funny and leading us to believe the dark matter is a contributing element to what keeps galaxies together. So we'll talk about all that much later, but this is our basic tool that takes care of that. Gravity can also do this. Very strong gravitational field slows time, so the light coming out loses energy, and its frequency stretches out that way. And so you see things gravitationally redshifted as well. You got to suss all that information out when you're looking at things in the universe. But for the most part, gravity doesn't have on a big scale, and around just everyday stars, doesn't have that much of a contribution to the red Doppler shift.
Is there a way gravity can blue shift something, or some equivalents? Not gravity per se, but maybe some other thing?
Yeah, if you were down in the gravitational well, so if you're down, close to the event horizon looking out, light coming in would be definitely gaining energy, yeah.
It's actually an important factor in GPS navigation.
That's true, yeah.
The radio photon drops inside the gravitational well,
Mm-hmm.
and it gains energy.
Yep.
It has to be accounted for by shifting the clocks on the satellites.
Exactly. So these take into account general relativity equations, and if they didn't, then they'd be off in just days, I think. We'd start to have pretty significant errors build up.
Yeah, that's more like general variables.
Right, Jenny, yeah.
And then the photon in the well is a constant offset.
Yep. So you can look at your spectrum of an element of interest in the laboratory, and that would be your at rest frequency position. If it is moving away from us, then it gets redshifted. All the lines, even though they are the same distance from each other, now head in the red direction. If it's moving at a greater speed, you get more of a shift. You can see how this is a very bluish. We're even showing this as a greenish color to illustrate what's going on here. This green now becomes yellow. This red is an even deeper red. If it's moving towards us, then this blue becomes violet, and this green becomes a darker green, and this orangey red becomes a little more orange. And moving towards us very rapidly, the line becomes very purple, kind of a teal, and a yellow-orange there. Now, the spectral lines themselves don't have color, and we're adding this in as an illustration. But yeah, that's a lot of information right there to be able to, yeah, question?
So if you were looking at these emission lines, how would you determine that it was still the same element but just moving closer or further away rather than interpret it as a different element?
Fantastic. It's the relative distance. The distance between the fingerprint itself stays rock steady. So, yep. And so that's how quasars, we'll talk about quasars, are moving tremendously fast from us because they're very, very far. That's the expansion of the universe doing that. And the shift was so far out of expectation that the astronomers looking at it just couldn't make sense of it. And I don't remember the astronomer's name, maybe it's in my notes here, who first went, wait a second, maybe that's hydrogen way over here, and looked at all the relative spots and went, my gosh, it's way over there, and did the calculation. That is unbelievably fast. And it was beyond what they expected could ever be seen of distant large objects. But once they figured it out, suddenly, boom, the universe was expanding on them, and it was a big paradigm shift in astronomy. So, but that relative to each other information is the critical part. Other questions? So, you get a remote laboratory with light coming from stars. You can get their temperature, composition, the density by the spreading of the light, the lines. Their motion, their rotation. If there are multiple bodies, you'll see, if they're going around each other, you'll see lines go back and forth due to Doppler shifting, and you'll see different lines at different shifts if they're made up of different components or different temperatures, different masses. You can see exoplanets in their elemental contribution. We're trying to get the atmospheres of exoplanets because that would be a different emission or absorption line. If it's emission, if it's off to the side of the star, absorption, if it's in front of the star, off of the light from the star itself. Magnetic fields broaden the lines as well. And interstellar medium and atmospheres around the stars are all probable by this information. That's a lot of information from a little bit of light coming from a twinkling star off in the universe.
I have a question on that last slide?
Yes.
All this is done at essentially 1 pixel on an image, right, in a telescope.
Well, they smear the light out with a spectrograph.
But that's in the frequency domain.
Right.
There's no spatial resolution.
No.
It's all 1 point on
Correct.
on the CCD image.
Yeah, that's every star is a single point of light. Yeah, sorry. Well, George Bush there. George Bush Sr. So, yep. Now we have, in a few cases, like Betelgeuse, we've been able to actually image the face of it and see sunspots on it. So we have a few large nearby giant stars we've been able to resolve actually. Yeah, but that's pretty unusual, yeah. All right, so now we will go to our sun, because it's the easiest star to study, and then work our way through stars in general. And then we'll work through the birth and the death of stars. So we'll go from our sun to black holes in this section. This will take probably this month and next, or maybe even the following to get through all these. We'll see. We are just about 10 minutes from the top of the hour, so let's take an early break, give you a moment to rest. We'll pick it up in 10 minutes and plow into the sun from here. Any thoughts or questions? Your hand is halfway up? No? Okay. I'll go pause the recording here and turn my mic off. So I will look up a little section and create a little section on orbitals just for fun, because you got me curious. And, well, because it'd be good to add that in there, talk about what the orbitals mean to chemistry, because it's all chemistry, but then the quantum mechanics behind that. Just written simple, we'll come up with a one bullet point reason for it, if that's possible. All right, so from our sun on to black holes. The sun is an average star. There's a quote I could bring from Douglas Adams at this point about an ordinary planet around an average star in a backwater or something like that, but I don't have that committed to memory. Mainly hydrogen and helium. It's in a balance between downward polar gravity and the outward polar pressure, and that works as long as there's an energy source in the center of the sun to provide that outward pressure. And for most stars, that's a very stable process for a very long time. It's in the middle of the field for size, temperature, mass, and life. And we'll talk about all this later. Again, it's a G2 classification star. I might have this in the upcoming slide, but everything beyond hydrogen and helium, lithium, oxygen, carbon, iron, all these other elements, astronomers kind of lump in together, calling them metals. So I know silicon is not a metal.
Do you know what the history of that?
The word metallicity and the metallic, well, it's just like saying something is red or red shifted. Well, it may be blue in just a less blue end of the spectrum, but it's still red shifted. It's just a very broad way to do it. But I don't know the history of where metals come from, So here's our downward gravity and our outward pressure. We have distinct regions based on the what's going on and the density of the material, and we'll talk about that momentarily. Near the center, at the core, pressures and temperatures are high enough that we have nuclear fusion going on. Fusion is light stuff pushing together to become heavier stuff, fusing together. That's the opposite of fission, which you have a heavy thing like a uranium nucleus that you're breaking apart, like billiards, and getting energy out that way. We get a tremendous amount of energy from this. About 4.7 million tons of hydrogen is converted into helium per second, and there's a little bit of extra energy released when helium is made. It turns out to be 3.9 times 10 to the 26 joules per second. Now, the inside of the sun is very dense, and the photon leaping from nucleus to nucleus, atom to atom, even though the ionization is really high, it takes a long time. It's a random walk to get out there, and it's possible that one photon might make it from the center all the way out in a few seconds, but on average it takes about 500,000 years by estimation for a photon to make it out. Yes?
These collisions, are they truly collision, or are they quantum mechanical?
Probably quantum mechanical, yeah.
So it's not just a photon hitting
Right.
an atom and
Yeah. Everything on this level is truly, yeah. We have a non-quantum or classical picture that we make in our mind because it allows us to visualize what's going on, but it is weirder than that.
That's different than, say, light pressure you used for a solar sail.
Correct. Yep. So we have convective zone above a radiative zone. The radiative zone is where pressures are so high that the material doesn't move around. Above that, you do get a layer of the sun where the gases are circulating up and down, bringing energy up mechanically. It's a convective zone, very much like thunderstorms. And then the visible surface, what looks like the surface of the sun, is the photosphere. So here's our core in red, where the nuclear fusion is occurring. Then you have the radiative zone, where that light has to go bouncing around. Then you have the convective zone, where the energy is lifted up. It can be transmitted radiatively as well here, but now you have convection bringing material up to this photosphere surface. And then out here you have this transparent corona, but the density difference between just below the photosphere and just above the photosphere is very, very little. It's very close to a vacuum. So it's not a surface. You gotta kind of erase that from your brain. In fact, the density 10% of the way down, if I remember this correctly, 10% of the way down is about 1 Earth atmosphere. So you could fly an airplane through the sun about 10% of the way in. Of course, you really got to worry about the heat. I mean, get that air conditioner cranked up. So it's only 6,000-ish degrees Kelvin, yeah. So this is very close to a vacuum here, even underneath the surface of the sun.
So is the photosphere a consequence of what's going on inside?
Yeah, I mean, it's the top, as we see right here, the top of these convective circulations, when they get to the surface here, they are the hottest. So you get the much hotter, yellower. Remember, the higher the temperature, the more yellow or bluer it is. So these little yellow spots here, which are about if I remember, they're about the size of Texas, are the hottest, and then that material sinks back down, and the sinking down zones are cooler because they've given up their energy to radiation that's gotten to your eye, are the redder, oranger veins in between.
Yeah, so my real question is, are there stars that don't have a photosphere?
I don't believe so.
Have like a superheated star or something?
Well, neutron star probably, so degenerate matter like that. But we'll talk about those. There are stars, the really big stars don't have much of a convective zone. They're radiative all the way through due to their pressures.
So if I understand what you said correctly, at the density of material from the photosphere to just above the photosphere, there's very little difference there. But there must be some transition going on there in how light is scattered or whatever, and it makes it appear as a surface.
Yeah, it's the point in which electrons can start settling down and creating neutral gases again, so light can transmit through. So,
It's a place where it's transparent.
yeah.
So when you go from plasma
non-plasma state. The temperature gets lower.
Same thing happened in the early universe. The cosmic microwave background radiation is the point where the universe itself cooled to where it became transparent. And before that, the density difference really wasn't any different, but you had temperatures high enough that light couldn't travel freely. You know.
So the photons are traveling more and more freely as they rise to the surface, and sooner or later, I guess right about here.
They can leap and make it 93 million miles in 8.5 minutes to you. Yeah.
Well, at least that's what the simulation says.
Thank you very much. We just can't get rid of from last night, huh? I can't. I can go home and binge watch more Elon Musk interviews. So this is less than 500 kilometers deep for all this end stuff here, really low density gas. There we go, yep. 10% of the way into the sun's air bring us to an atmosphere. My brain remembered it, yay. And these are, size of Texas. I should read my own slides instead of, and these little convective bubbles last for about 10-20 minutes before they're replaced by a different welling up of energy.
So what causes the darkening?
Cooling.
It's just different darkening.
It's Wien's law. Once it cools, then the peak radiative frequency is now a redder
So any
part of the
convective
spectrum.
process, you're doing that heat transfer, turn it over.
Yep, exactly. Cool. It's the same stuff we see in thunderstorms here in the summer. So you got too much hot heat from below, goes up, cools, releases energy to the upper atmosphere. You can see that in satellite imagery, and then the energy comes down every place else. Yeah. Or the atmosphere comes down. I said atmosphere, yeah. Sometimes I don't know what I've heard myself say. So above the photosphere, you have the chromosphere. This is the next layer of atmosphere up. This is what we can see around the moon and during a lunar eclipse. I'm sorry, wow, that's totally wrong. It should be solar eclipse. Or from space, fix that slide. And the temperature soars here to 10 or even 10,000 to 1,000,000 degrees or more. And that is an area of study here of how this gas gets excited to temperatures so much higher. Now you're at a much lower density, you're going even further into the vacuum of space. And so there's less material to work with. And so if you pump energy into it, the fewer atoms will get excited more. There's more room for them to move around. We think there might be a link between these little flame-like structures injecting information, stop it, energy into the chromosphere, but this is an active area of research right now. There's the chromosphere. I've got to fix that slide tonight. Not during a lunar eclipse. What on earth? So beyond that's the corona. This extends out into the solar system and is also a very good beer. Temperatures rise even further, 3 million Kelvin out here. And you can see bends in the sun's magnetic field and huge hair-like appearances around. Yeah, it says total solar eclipse this time. These ionized atoms become what's called the solar wind that blows past the Earth at 300 to 800 kilometers per second, sometimes gusting to 1,000 kilometers per second, all the way out into the outer solar system. And eventually this interacts with the interstellar medium around our solar system. And we're waiting for Voyager to definitively give us some information as to the picture of what this bow shock or this boundary looks like. And we've gotten some information back on what the outer extent of the sun's atmosphere does beyond our solar system. But we are all swimming in the sun's environment very distinctly deep in the inner solar system where the Earth is. Hence all the aurora and cool things we have. We'll talk about those later. Other stuff we can work with the sun. The sun acts like a three-dimensional bell and is ringing with a certain harmonic here, and we can detect that using Doppler shift of the surface, and we get these definite probing of the internal structure of the sun in a way that we kind of do with earthquakes here on Earth. Earthquakes, you get the energy traveling through and then emerging around the rest of the Earth, and we can see how the waves interact with the interior and pressures and boundaries and things that arise. And helioseismology gives us some confirmation of what we think is going on inside the sun. But probably the thing people most think about as an interesting features of the sun, other than being really hot, is the sunspot idea. These are cooler areas on the photosphere. They can be down as low as 4,200-ish Kelvin. They appear dark only in comparison to the whole disk. If the entire sun were, I think I got that on a slide here too, if the entire sun were a single sunspot, which can't happen, it'd still be awfully bright. But in comparison, because of Wien's law again, it's a cooler region, so it's giving off a redder light, from your point of view, I'll move it that way, redder light and less energy. The peak is lower on Wien's graph there. And so we have what looks like dark spots. These are the endpoints of magnetic loops. We have very, very powerful magnetic field generated by the plasma flow inside the sun. How that's generated, maintained, and what's going on over time is it's an area of science called magnetohydrodynamics. It's mixing fluid flow, plasma science, and the science of magnetic fields, and it is really complex. But you can see these hoops of magnetic field lines bringing along hot gases that allow us to see it because they're emitting light as they cool. So we get very hot here and then becoming redder as they cool up here, radiating their energy away. So there's new stuff coming up this side as well. So visually you can see Wien's law telling you something about how the gases, superheated gases, are flowing.
So is the way to visualize those loops, things are coming out both ends? And
Yeah, there's a north and a south side, just like
solid
a,
particles just going up one thing, down in the other.
Right.
As a current.
right. Yeah, it's not exactly the same as the current. Yeah. So these sunspots are located in the photosphere. They're darker because of the black-body spectrum, temperature. Brighter than the full moon, but have an orange-red color if the entire sun were a sunspot. The quiet sun is pictured here. Here is from just a couple nights ago, and you can see we have a very quiet sun. We do put numbers on sunspots and sunspot groups, but is it that one right there? I don't know. They're stretching it. I really want a sunspot. Yeah, the sun is pretty ridiculously blank right now. When it's active, it can look like this. Tremendous clusters of sunspots. Here's the relative size of the Earth. They can be 3, 4, 5 times larger than the Earth. The sun is big. So I think, what is it? You can stretch 218 Earths across the face of the sun and fill the sun with 1.3 million Earths by volume. So when we plot the location of sunspots over time, so here's 1955, 1975 in this diagram, a very, very nice representative stretch of time. The sunspots start out few in number and kind of high in latitude. Here's 40 and 50 degrees latitude. Just like on Earth, the poles north and south are positive 90 and negative 90 degrees, and the equator is 0. Use the same coordinate system on everything out there. And then as the time goes on, the sunspots become more numerous and migrate towards the equator. So when you look at a chart over a few decades like this, a couple decades, you get these butterfly-looking patterns. So it's a butterfly chart. I mean, it's kind of easy to remember. This would be one solar cycle, sunspot cycle of about 11 years. And then north and south reverse, and the pattern happens again with the north and south of the magnetic alignment of these things reversing. So you sort of get a 22-year cycle considering the polarity of the sun. You can go from, like right now, close to 0 sunspots to 100 or more sunspots at a time.
Is solar maximum, where are most sunspots the maximum?
I think the maximum would be right about in here, yeah.
Yeah, you have to integrate that clockwork.
Yeah. Because they fade out, you get a minimum right in there, maximum right. Yeah, the graph on top is really interesting. We're going to expand on this a lot in the next few slides. Yeah, here is from the 1600s to the 2000s. You can see that the number of sunspots vary. These are all sunspot maximums, obviously, with the graphs. The top is sometimes maximums are pretty low, or like this stretch right here, there were none. And you're lucky enough to live in another stretch, it looks like, beginning where we have virtually none. So here's 400 years of sunspots. This is a lot easier to see. And this stretch right here is the Maunder minimum. Galileo saw sunspots and put that in his journal, and shortly after that, sunspots went away. And so I kind of, well, you were seeing spots. But they were there. He wasn't seeing things. We had.
He stared at the sun too long.
He did. Yes, he did. So we have here almost a century of quiet. The Dalton minimum here, named by the astronomers who kind of suss these out of the data. So if you discover something cool in astronomy, you get a name after yourself, so keep that in mind. And we're just recently had what's labeled the modern maximum. I guess Franklin or whoever was what astronomer didn't get in the naming convention. You could have called that the Ainsworth maximum, but no, I didn't discover it. We can reconstruct sunspot data from indirect indicators of isotopes of, gosh, I'm trying to remember if it's nitrogen or carbon, but going back to 10,000 BC, we can use secondary indicators and kind of piece together what might have occurred there. We can see this, let's see, quiet spot here and quiet spot there. So large variability going back over time. Looking at the Dalton minimum in present, this is a little older, but you can see declining sunspot maximums into a quiet period, and we're definitely in another quiet period here. So March 2015, we went down, then went up to a very anemic sunspot maximum. Here is going into January 2019 extrapolate. This is the forecast, and you can see up to 14 or so. It wasn't even quite getting up to what we were expecting. So the sun is definitely dropping out. Adding some more data, taking us up into 2017, I guess, almost into 18. You can see the forecast now is for it to just fizzle out to near zero and stay that way, with a very small maximum in 2014. So lots of debate whether the Little Ice Age from 1430 to 1850-ish was caused by a low number of sunspots. We had a dip in here, 1645 to 1715. So whether that or other factors contributed to that, some recent papers have come out saying that there is not a climatic forcing that's significant between sunspot numbers and climate. It seems odd that if you have few sunspots, the sun should be brighter. Why would the Earth get colder? But the thinking was that the overall energy output of the sun drops a little bit. But now we have spaceborne platforms that have been up there staring at the sun, measuring the actual energy flux from it, SOHO and back, from the maximums into the current minimum. So we're getting really good data of what the sun is actually putting out. Because looking at the sun through the atmosphere, you get a lot of other things coming into what's happening. I mean, the atmosphere's opacity changes what you see on the ground level. And so when you're trying to get just 1% or 0.5% of sunlight figured out, whether that's an atmospheric effect or the sun itself, is very hard. So we needed stuff in space. We've got stuff in space. The data is coming in. What we think is going on that causes sunspots is basically we have this, in the quiet time, a nice uniform or largely uniform magnetic field stretching from north to south. We know that the sun rotates differentially, that the equator rotates faster than the poles. I think it's like 28 days at the equator and 33 days near the poles for rotation. And so with that faster rotation at the equator, the magnetic field lines get ahead of their locations at higher latitudes, and so it starts to wrap around and eventually short circuits, taking a shortcut to reconnect, and that altering in the magnetic field line you see on the surface as the loops coming out and the sunspots forming. So why the sun becomes quiet like that and can remain that way for a century, so 9 to 11 sunspot cycles going by without anything happening is a bit of a mystery. I think I've seen some things in the literature that there's different things happening at depth. And so you have a vertical component to the magnetic field and sheets of magnetic energy, but you're beyond my pay grade now. I don't know if I can push any further than that.
Does the sun's magnetic field flip between solar cycles?
Yes.
So the north and south pole reverse for the same reason that the Earth splits occasionally?
We occasionally do, yeah. We do it on the order of many thousands or years, but yeah, the sun's much quicker, yeah.
Another thing just to notice about sunspots, because that's what makes the atmosphere, while they're darker, cooler, they're very, very hot in the extreme ultraviolet.
That's true, yeah.
And they put out more energy net.
Yeah.
The sun puts out more net energy.
Exactly.
Because they're very, very hot in the extreme UV. So there's actually more energy coming.
There is more energy coming, even though the sun, looks darker. Yeah, you're absolutely right. Yeah, and people have taken sunspot numbers and tried to link them to birth rates and the stock market and oil prices and wars, and people have taken this data set and tried to put it to everything possible, but I've never heard anything convincing.
It all correlates to about 0.5. It all correlates to about 0.5.
Right, exactly. Thank you very much. So prominence in flares are huge loops. These are the famous, often pictured solar storms. If you wanted to show disasters in 1950s sci-fi movies, you'd have some shaky telescope image of a solar hoop, like, ah! We're very nicely protected here by the Earth's magnetic field, and But it makes beautiful things called aurora, aurora borealis in the northern hemisphere, aurora australis in the southern hemisphere. We do get coronal holes. These are parts where the loops keep going through the photosphere. The energy that gets released by these storms definitely affects radio and communication here on Earth, kickoff of aurora. But just the solar wind itself will do that as well, and also the orientation of the Earth's magnetic field in the plane of the solar system does it. So I think in the spring and the fall you get more aurora just because of our more neutral alignment with it. The sun does create ozone. Ultralight in the upper atmosphere, the stratosphere, is heated by incoming ultraviolet radiation and the interaction with oxygen. So the temperature in the stratosphere rises again, creating a stable layer that's the cap, the top of the weather portion of the atmosphere, the troposphere. And so airplanes like to fly in the lower part of that because it's smoother. You're not bumping around in the in all the convective cells in the troposphere because of that. But and we have the lots of people have worked with sunspots and weather, and again, there's just not a strong correlation with these. We do have the Milankovitch hypothesis that links orbital variations in the Earth's motion around the sun. We have the precession of the axes, we have the axis tilt changing, and orbital variations are where we are close and far from the sun compared to the tilt of the Earth. And all that seems to have a stronger correlation to long-term climate variability and ice ages and things like that than sunspots.
What were those pictures on?
This is a close-up of the photosphere where you've had I think a coronal mass ejection event occur, and this is a shock wave traveling out in the sun's atmosphere. Yeah. Kind of cool, huh? Yes, it is. Much bigger than the Earth. You don't want to be there, so that would be a bad place to be. All right, is there any questions about our sun before we go on to other stars? This is our model. We have our close by laboratory of an average star here, so now we can go out into the universe and see what other stars do and how they differ. But any questions? I know I've left you with more dangling sunspot questions than you had before. But. All right, so the sun is about 8.4 light minutes away from us. The next nearest star, Alpha Centauri system, with Proxima Centauri being the closest of them, about 4 light years away. Light year is just about 6 trillion miles. So if you do get that in your brain, 1 light year is 6 trillion miles. So just a nice rule of thumb to be able to spit out at a cocktail party. I'm going to a cocktail party this afternoon, so I'm ready. It's actually, yeah, it's American Heritage Girls potluck, so they may not be talking about this. But what we need to do as we go out into the universe, first off, is figure where everything is around us. This 8.4 light minute distance we conveniently call 1 astronomical unit. Now, the Sun-Earth distance is not a constant. We are closest, as we talked about earlier when we talked about the reason for seasons, we are closest in the beginning of January and further in the beginning of July. So when you're sweating on the 4th of July, you're actually further from the sun, go figure. But the average distance is 1 astronomical unit, about 93, 94 million miles. And so once we get this really well established where we are with respect to the sun, then as we move around, we can develop our first tool for measuring out into the universe. And eventually we're going to use a step ladder of techniques to get us all the way to the most distant quasar and the cosmic microwave background radiation itself. But you got to start someplace, so we'll start in our solar system and work out. The early astronomers used errors in the position of the Galilean moons, the big moons going around Jupiter, to help narrow down the speed of light, which we also needed for to piece together our place in the universe and the time it takes things to occur. So all this is important local work that lets us go out into the universe. So just like I said last night with the parallax, stellar parallax is the first thing that lets us measure out. And I did this, so everybody put your finger up in front of you. Nobody did it last night either. And if you switch your eye from one view to the other, you'll see your finger pop back and forth. That parallax is what your brain automatically uses with your two eyes to give you the nearby distance to toss a ball or walk up to and stop and like that. So as we go around the sun, a nearby star here seems to move a tiny bit against the much more distant background stars. If you assume the bright stars are close and the dim stars are very far, then you've got a first brush tool to do this. Now maybe you're wrong. Maybe a bright star just is intrinsically bright and it's very distant, and this technique won't help you as much as you expect it to. But measure a lot of stars that are bright against a lot of dim stars, and eventually the ones that are oddballs will get figured out, and you can figure their distance as well. And you can discount the ones that are dim but close that are also messing up your estimations. So this stellar parallax lets us see like this little pink star here is the nearby star, and in January it's over here in this pattern, and in July it's over here. So that's an extreme version. It's very, very subtle effect, but early astronomers were able to measure the parallax of a lot of stars right off and start to figure out how big the universe is. We can use a very simple equation here to get distances. In astronomical units, you can take 206,265 divided by the angle you see a star shift by to figure out its distance. We came up with a unit of measurement called the parsec, because the parsec makes this equation very simple. Parsec is defined as a distance that a 1 astronomical unit shift results in a 1 arc-second wiggle of a star. And the way I always say it is, if you took a fluorescent tube and you stretched it between Earth and the sun, so we got 1 astronomical unit long fluorescent tube, and you just move it out into space until it only subtends, is that the right word? 1 arc-second. Remember, 360 degrees all the way around the sky. This is your degree measurement. Take one of those divided by 60, you get 60 minutes of arc. Divide each of those by 60 and you get 60 seconds of arc. So this is a very tiny thing. But if you move that big, huge light bulb all the way out there till it's 1 arc-second wide, it is 1 parsec away. And a parsec turns out to be 3.26 light years, which is pretty close to how many feet are in a meter, so it's a way to kind of keep those numbers in mind. From the ground, you are limited by the blurring of the atmosphere, and for much of the history of astronomy, the limit was about 0.02 seconds of arc, which allowed you to get out about 50 parsecs, or about 160, 170 light years distance. We put up the Hipparchus satellite. That was able to go down to 0.01 seconds of arc, It allowed us to measure the distance of 1 million stars. That program ran from 1989 to 1993. And I mentioned it last night that the Gaia mission is going to be able to push this to 0.00002 arc seconds, pulling in 15th magnitude stars. It can go down to 0.0002 arc seconds for 20th magnitude stars. And we're going to get a 3D map of nearest billion stars around the Earth. Still, that's only 1% of our galaxy. So we're very limited on what we can measure. But as we'll see, this is the first rung of our ladder of figuring out how big the universe is. So the more accurately we can measure the actual distance of all of these nearby stars from us, the more we can figure out an awful lot of other stuff, including mysteries like Tabby's star out in the universe. Because we'll get to this in just a little bit, but a star of a certain brightness, if you knew its exact brightness, you wouldn't need any other measurement to figure out its distance. You just look at how bright it looks. As long as there's not gas and dust in the way, blocking some of the light, like last night, Tabby star example, a quarter of the light doesn't reach us because of interstellar gas and dust. You can get its distance just by looking at its brightness. Just like street lights all have the same brightness. A distant street light's a little teeny light, and if you measured it, you would be able to figure out how many miles away it is just by how much light is still reaching it. So it's a simple relationship.
So on the Gaia,
Mm-hmm.
so that 0.00002 parsec, am I right, is that the number of parsecs then that you can, how far away is at that amount of parallax?
Oh, how distant out?
Is that 20,000? Is that 20,000 parsecs? Is it a reciprocal of that?
Let's see. Yeah, you'd flip it. So 0.1.
1,000 times the first equation is 50,000 parsecs.
Yeah. Is that right?
No, it's 50,000?
Yeah.
0.02 seconds.
Right.
Parsecs, then
Yep. So you're multiplying by 100.
1,000.
So 50,000 parsecs, so you'll be able to get about 150,000 light years.
Yeah. And the diameter of our galaxy is about 150,000. So that'd be the entire galaxy, not just 1%.
So they can measure the galaxy. I mean,
Yeah, I don't think that.
distinction,
Yeah, there's something.
They could measure the distance of all the stars in the galaxy if it weren't dust.
I'll have to look into that. Yeah. I think I got this from the Gaia site, but yeah, I didn't.
Sounds amazing.
It does. Maybe too amazing. Yeah. Right. Extraordinary claims need extraordinary evidence. So, yeah. All right. So we'll put an asterisk by that. See if those numbers are correct. So yeah, it's just I was talking one slide ahead of where I was. See, the apparent brightness, how bright a star appears from Earth, is usually given the little letter m. That's the magnitude that you can look up on your standard star chart or now astronomy app. The actual brightness, its intrinsic brightness, we give it is based on the flux of the energy coming from the star. Each 2 times out, you get 1/4 the flux. It's just the inverse square law. So we give that a capital M as being the actual brightness of the star. And what we really want to do is we want to compare all stars with each other. We don't want to be all Earth-centric about it. So the little m magnitude is just good for your backyard astronomer or the professional astronomer. The capital M lets you see how stars actually compare with each other. And so we just made up a standard. We imagine bringing them all to 10 parsecs distance away from us. And little v is for visual. And we call that the absolute magnitude. So capital M is its intrinsic brightness as it would appear from Earth 10 parsecs away. And so that is figuring both the distance and the luminosity of the star in. There's a little calculation. You take the magnitude, subtracted from the absolute, subtract the absolute magnitude, that equals -5 plus 5 times the log 10 of the distance d, and the distance d is measured in parsecs. So from that you can get the actual luminosity of a star. Really pretty cool. I mean, you got all those buttons on the calculator, so you can get that to go. Once we know the luminosity and we know the temperature from Wien's law, or from earlier, now we can figure out the surface area it would take to let that much energy out at that temperature. So as soon as you have its actual brightness and its temperature, you know its diameter, you know its surface area. So it's just the equation for the volume of a sphere. So it's photosphere diameter. So the luminosity divided by the luminosity of the sun equals the square of the radius of the star divided by the radius of our sun times the temperature of the star divided by the temperature of the sun squared also. So you got a very simple relationship here, now figuring out using light only the size of these stars that only look like single dots out in the universe. And that allows us to create one of the most important charts in astronomy, the Hertzsprung-Russell diagram, or the HR diagram, named after the last names of the two astronomers who put it together the first time. And what we mark here is the luminosity, so it's the luminosity compared to the luminosity of the sun. So there's our sun right there at 1. So our sun's luminosity divided by our sun's luminosity is 1, so it gives us the center of the graph. So when we say our sun is average, it really is. From the hottest to the coolest that we see out there, we're really middle of the road. And then across the bottom, you put temperature. So from the blue-white hot temperatures on the far left to the very cool temperatures on the far right, reddish colors here. And they just started plotting everything that they had. Just put it all down there. And surprisingly, most of the stars in the sky fall along this sort of lazy S shape. This is called the main sequence. Got the little red dwarfs down here up through our sun up to the big blue-white monsters. And then as we work through the material over the next month or two, we'll see stars that die often head off into this direction. They swell up and become red giants or supergiants. And then they either puff off a lot of their atmosphere and their remnant core shrinks down to be these little white dwarfs who just cool down over time. Or something much more violent happens up here, and we'll go from there. But you can see in a glance, there's order in the universe. These stars are just not all over the place. And I don't know. I'd love to see a book on Hertzsprung-Russell diagram and see what they were expecting when they started plotting stuff, if they thought they were going to get some organization, or why other astronomers hadn't done it up to that point. I don't know.
I'm confused about that diagram. Why are some stars brighter than others? Is the luminosity taking the size of the star out of the equation?
No, because these are intrinsically a lot more luminous. The bigger stars are not only bigger, they're also a lot hotter, putting out a lot more energy per time, and their Wien's law curve is much higher, so the area under the curve is much higher as well. So they are much more luminous.
So I guess I missed, luminosity really is a measure of the size of the star, not intrinsic brightness. I mean,
Well, those are directly related to each other. Yeah, going back to here, luminosity radius and temperature are all directly related along. Yeah. So bigger stars are more massive, hotter, larger, and more luminous, all at the same time. And the dim stars are the reverse.
So is luminosity something like the number of photons per square meter coming out of the sun? Or am I misinterpreting that number?
No, you're correct. It's the flux, yeah.
It's not per square meter, it's you got to integrate it over the surface of the sun, that star. Because it's no luminosity.
Is it integrated over the soul?
Yeah, where
It's
did
not per square meter.
Well, isn't that the big
the
end?
brightness is based on the flux of energy, which is joules per second per meter squared, or watts per meter squared.
That's the luminosity. No, that's the intrinsic.
That's intrinsic
flux.
brightness, yeah. That's the flux. Okay. So here's a little more artistic version with some stars in here. And what we've done is we've figured out that the very dim stars have a very small fuel source. There's not much of a star there. But they also have a much smaller core where nuclear fusion is occurring. And so there's much less hydrogen being consumed, but that also relates to much less energy coming off of the star. And so we have put together, looking at star clusters, and we'll see how that's done later. You can plot star clusters and figure out that the bigger stars have left and the smaller stars are still in the main sequence, and you have a turn-off age in the star clusters. So we've been able to piece together the average lifetime of stars all the way through the main sequence. So down here in the, remember this is the OBAFGKM. Oh, thank you very much. OBAFGK. I should look at my own slides. The spectrum right here, the stellar classifications, heading on down here, that the K and the M type stars are going to last 10 to the 11th years and more. Yeah, trillion-year life spans down here for these dim little red stars. Up in our sun, we have on the order of 10 billion years or so. And we're right about the middle right now, with the Earth being about 4.5 billion years old, and the sun being about 5.5 billion years. And it's got about 5.5 billion years to go. Then you head on up here to the big monsters, the O-type stars, and you got 10 to the 7th years. So you got 1, 2, 3, 4, 5, 6, 7, a million years or so for the entire star. So the O and the B stars live fast and die young. So they really are like movie stars. They have rough, fast-burning lives, and the rest of us live quiet, long lives down here. Eventually, these head off into the supergiant area. These stars, as they age, head up into the giant area, then your white dwarf region down here, the graveyard of the middle lower mass stars. And we'll talk all about those in the sections to come.
There's not many there because they're hard to see.
Down here? Yeah. This doesn't imply number. We just have a couple notable ones here. So Sirius B and Procyon B. There's a lot. We know of a lot of white dwarfs out there. Maybe they don't all have proper names. So we do, for, again, historical reasons, call these dwarf stars along here, even though some of these are definitely not. Their lifespan comes and is related to their mass. Mass is related to luminosity. Luminosity is related to the size, and everything's all this nice organized pattern across the middle here. The other branches, giants and supergiants, are the future evolutionary phases of stars as they die. We'll get into those. To get the masses of the stars themselves, we have to go all the way back to Kepler. We talked about Kepler at the beginning of the course for a reason. that if we have binary stars, especially if we have two that have a different spectral classification, and multiple stars are very common. 2 of every 3 stars are multiple stars, so it's like love and marriage. They like to come in couples. They revolve around a common center of mass. The ratios of the masses equal the inverse of the ratio of their separation. So we can figure out how far apart they are, which we figure out by how long it takes them to go around each other. We can figure out the total mass of the system. The total mass of the system is the separation cubed divided by the period squared. Separation in astronomical units, period in years. We're all Earth-centric in units here. We can piece that together and then get enough systems, you can start figuring out how much stars weigh. Again, just using light. It's amazing, but there's order of the universe out here. We can see spectroscopic binaries to get even a larger pool of stars that go around each other. So we can look at these spectral lines shifting, Doppler shifting opposite of each other as they go around. They have to be somewhat in line of sight. If they're straight edge on, that's the best, but even if they have some component of tilt towards us, we can get information from that system. We just have to kind of figure that out later. The chances of every star being like that are calculable, and it's a small percent. But eclipsing binaries like this give us the additional data points of the light curve. So just like looking for planets going around each other with the Kepler mission and other missions and ground-based techniques, stars going around each other give us information about the 2 stars that way. We can get their radius that way. We can get how extensive their atmosphere is by how fuzzy the sides of the light dip are. Algol in Perseus is a famous eclipsing binary, known even to ancient people. That's an edge-on system with a star that eclipses the main star, causing a big dip. The star goes down every 2.5 days, I think, in brightness for about 9 hours. We had an astronomy lab that we ran at ASU that students would go out and measure the brightness by looking at the stars around it and rating. We had a little chart with their magnitudes on, and you would just kind of guess, okay, it's close to that one, it's close to that one. They'd make the chart and they get the light curve of Algol, the Ghoul star. So again, I see I'm a slide ahead of myself already. Eclipsing binaries, you can see the size of the star by the time it takes for one star to cover the other, and vice versa. With the temperature, spectral type, and masses figured out, we can really get a complete picture of these stars. And once we get more and more stars that are K and G and O type figured out in mass, and we can really piece the entire thing together. We have a direct relationship figured out between mass and luminosity now. Luminosity is the mass to the 3.5 power. It's easier to make little stars than it is to make big stars because you don't have to have as much material. It's just like looking at exoplanets. We got a lot of Jupiter size and bigger exoplanets out there, but they're easy to detect. It's much more easy to make Earth size or Mercury size planets because you don't have to have as much stuff. So even though the number of discovered Earth and Mercury sized planets is really tiny compared to Jupiter size, we know they're out there, but we see the same relationship with stars. So the M classification and the K classification of stars, there's a lot of them. They're small. They also live really a long time. So ease to make and long life means you're going to have a tremendous number of M-type stars out there. As you head up from M up to O, the numbers trail off, And then as you go up in luminosity, you can see the O-type stars are not even really plottable up here. Supergiants and giants are not very visible. But you can see these guys across the galaxy, even into other galaxies, much more easily than you can these because they're so much brighter than the M-type stars. So again, a Hollywood analogy is pretty good, that you don't have very many superstar actors, but everyone knows what they're doing and they're in the tabloids, and whether they ate at a restaurant last night is something you can find out. Someone like me, you're not going to be able to find out unless I post on Twitter that I ate at Denny's last night. It's just I don't have paparazzi following me. So these big, bright, luminous, short-lived stars are the things that make up a lot of what we see when we look out at great distances in the galaxy. But it's a disproportionate visual sample. All right, going back to the hoarders mentality in astronomy, population 1, 2, and population 3 stars, in my mind, are mislabeled, they're backwards. Population 1 stars are the metal-rich stars like our sun. These are second or maybe even third generation stars in which earlier generations of stars have blown up, generated and spewed out heavier materials. And these are common in the spiral arms of galaxies. Population 2 stars are metal-poor stars found in the galactic halo. And hypothetical first stars are population 3 stars. These would be almost entirely hydrogen, helium, a little bit of lithium mainly made from Big Bang material itself. We are working hard, especially with the James Webb Space Telescope, to start getting good images of stars back this time. I would just name them the opposite direction. Earlier would be 1 and later 3, and if you have some other classification you want to add on, you could call that 4, but I don't know.
So I've heard that the population 1 stars, like our sun, you mentioned 2 or 3 generations, the material, 2 or 3 generations of stars,
Mm-hmm.
so like 10 or so.
Mm-hmm.
Do you think that's, do you know anything about that? I mean, the material in our sun,
Mm-hmm. Right.
how many stars has it gone through? Since, and they're saying like 10 or 8 or 10.
8 or 10 generations?
Yeah, that's what I've heard, but I'm curious.
Well, I mean, with the universe being 13.8 billion years, our galaxy probably got its act together pretty early in that phase. And with the bigger stars only having millions or tens of millions year-long lifespan, there's plenty of time for a number of bigger stars to come and go, generating that stuff before we get to a smaller little metal-polluted star like ours, or metal-polluted like our solar system. I'm stamping on right now, yeah. So yeah, I guess it's possible. I've always heard 2 or 3. I haven't heard 8 or 10.
Yeah, I've heard more than that, but
Okay.
I'm not sure.
It probably depends on what star you're right? So there's one of those really big stars that only has a few million years
Right.
lifetime.
Yeah, and then you have like the update that I had from a few months ago, where we saw the gravitational waves coming from a neutron star merger, and a lot of the really heavy materials, uranium and lead and titanium and things like that, that we really couldn't explain well from these generations of light mass stars, supernovae and like that spewed out a lot of that stuff, and that could explain the amount of that. So we would have to have some of those big stars creating neutron stars, and the neutron stars merging and spewing that out, and some of that got into our formation as well for us to have as much as we do. So yeah, there's a more complex story out there. I don't think it's all been pieced together yet. So, but we're going to get into that. So any other thoughts here? All right, so star formation, starting with the interstellar medium, is like a whole new topic, and we are at noon now. So next time I will look at some p-orbital expansion and get into S&P orbital electron stuff and explain that. I'll take a look at the Gaia mission volume and try to figure that out for next time. So is there another pending question you had? I think those are the two big ones. Gaia mission, right. So I'll look those up and solidify my knowledge. But was it in Bill and Ted's Excellent Adventure that Socrates said that true wisdom is knowing that you know nothing. So that's me. All right, thank you all very much.